Good afternoon, everyone. Thank you for taking the time to be here. My name is Zach Matiko, architectural and outside sales rep for WR Meadows, covering the New York and New Jersey territories. And today we'll be talking about Green Roofing 101. So this session is intentionally geared towards architects. We're not just going to be talking about what green roofs are, but how they actually interact with your roofing and waterproofing systems, what detailing discussions really matter, where the problems tend to show up years down the road. And the goal today isn't to turn anyone into a green roofing expert. Instead, by the end of the hour, I would want you to feel more confident coordinating these systems, asking the right questions of consultants, contractors, manufacturers, and detailing assemblies that perform long-term without leaks or callbacks. We will be focusing on system concepts, design intents, best practices. If there are product-specific or project-specific questions come up, I'm happy to address those at a later date. So moving on in the agenda, here's basically how we will structure our next hour. We'll start with a high-level look at why green roofs are being specified more frequently and what's driving them, both from a regulatory and client perspectives. Then we'll walk through the main system types: extensive, semi-intensive, and intensive green roof vegetated systems. After that, we'll spend a good portion of time on what I would argue is the most important part of the conversation: membrane protection, vegetated-free zones, drainage visibility, and correct system layering. These are all areas where architectural detailing directly impacts long-term performance, risk, and liability. So jumping into it, why do we use green roofs? So green roofs used to be considered as a design feature or a sustainability add-on. Today, the trend is kind of steering towards that they're much often driven by performance and requirements. There are three primary reasons why we are seeing architects specifying green roofs, which are stormwater management, developer value, and human experience. Stormwater is frequently the first driver, whether that's a zoning requirement or it's a municipal regulation or an incentive to reduce on-site detention needs. The developer value comes next. Green roofs create usable amenity space, increase rental appeal, and in many markets support higher occupancy and long-term asset value. And finally, there's the human experience. Access to outdoor space, especially in dense urban environments, has become more of an expectation rather than a luxury. So in addition to some of those primary drivers and benefits, green roofs provide a collection of secondary benefits that are just as important from an architectural perspective as it is from a performance standpoint, even though they're often not immediately obvious in the early design phase. One of the most significant benefits of this extension is the extension of the waterproofing membrane's service life. When the membrane is fully protected and from UV exposure, thermal cycling, and physical abuse, its longevity increases dramatically. Instead of being the most vulnerable component of a building's enclosure, like that of a traditional roofing assembly, the membrane becomes one of the most protected part of the entire roof. For the owners, this can delay costly replacement cycles by many, many years. Green roofs also contribute to reducing buildings' energy loads by adding mass and insulation above the roof deck. These systems moderate temperature swings, reduce heat gain in the summer, limit heat loss in the winter, and this thermal buffering effect not only improves occupant comfort, but it also reduces the HVAC demand for your building enclosure, particularly on the upper floors. At an urban scale, vegetated roofs help mitigate urban heat island effect by replacing dark, heat-absorbing surfaces with living systems that cool the surrounding air through evapotranspiration. They also provide measurable sound attenuation, which can be especially valuable in dense urban or transportation-adjacent environments. Ecologically speaking, green roofs create habitat for pollinators and migratory species such as bees and hummingbirds, and in some cases can support productive landscaping or urban agriculture. When these environmental, energy, durability, and life cycle benefits are considered together, green roofs begin to look far less like an aesthetic upgrade and far more like a long-term building infrastructure that supports resilience, performance, and value over time. So now we'll go into the different types of vegetated roof systems, starting with extensive. So extensive green roof systems are typically the most common entry point into vegetated roofing, especially in commercial, institutional, and multifamily projects. These systems usually have less than 6 inches of growing media and most often use sedum-based vegetation installed mats, plugs, or cuttings. From a structural standpoint, extensive systems are attractive because they impose relatively low dead loads compared to deeper green roofing assemblies. This makes them especially well suited for large roof areas, retrofits, and projects where the structural framework is already fixed early in design and additional capacity is limited. Because the soil profile is shallow, extensive systems are not typically designed for regular occupant use. Instead, they function primarily as performance-driven roof assemblies. Their purpose is to manage stormwater, reduce heat gain, protect the waterproofing membrane, and contribute environmental benefits without walkable finishes. Permanent furnishings or complex programming. Another important consideration is maintenance. Extensive roofs are generally low maintenance, but not maintenance-free. The limited soil depth creates a more stressful growing environment for plants, which is why sedum and similar species are commonly used. These plants are resilient, drought tolerant, and capable of surviving with little or no irrigation once they are established. From an architectural standpoint, extensive systems work especially well on podium decks, low slope roofs, and large commercial roofs where green roof primarily to be viewed from above or adjacent buildings as shown in the picture on the screen now. When detailed correctly, they provide meaningful life cycle and performance benefits, including stormwater retention and membrane protection, while remaining cost-effective and relatively straightforward to coordinate with the roofing assembly below. From a design standpoint, the key is intent. Extensive green roofs excel when the primary goal is performed, stormwater energy and membrane longevity, not human occupation or visible complexity. When architects clearly align system selection with these goals, extensive vegetated roof systems perform very well and represent an efficient, durable solution. Here you'll see an example of an extensive pollinator habitat where you have the option to put a large palette of different plants and vegetation up on these roof systems. You'll most commonly see extensive systems on multi-tenant residential projects, commercial buildings, and institutional roofs, and also hospitals where stormwater management, energy performance, or regulatory compliance is more critical than regular roof occupancy. In these applications, the green roof is performing important technical work, retaining stormwater, reducing heat gain, and protecting the waterproofing system without being designed as an amenity space. These roofs are typically not intended for frequent floor traffic or programmed use, but that does not diminish their value or diminish the need for a vegetated-free zone, which we will get to in a couple slides. Even without regular occupancy, extensive systems provide measurable environmental benefits, including reduced runoff, lower roof surface temperatures, and improved thermal performance of the building enclosure. From an architectural perspective, extensive green roofs are more often practical solution when performance goals must be met without adding complexity, structure, load, or ongoing operational burden. They allow projects to capture many benefits of vegetated roof systems while maintaining straightforward detailing and long-term durability. Moving on into semi-intensive roofs. Semi-intensive green roof systems sit in the middle between extensive and intensive, both in terms of system depth and design opportunity. These systems typically use between 6 and 8 inches of growth media, which immediately opens the door to a much broader plant palette. With that additional depth, semi-intensive roofs can support grasses, perennials, flowering plants, and native species rather than just sedums. This allows architects to introduce seasonal variation, texture, and color while still maintaining relatively manageable structure and maintenance requirements. From a performance standpoint, semi-intensive systems retain more stormwater than extensive roofs and can create healthier growing environment for plants. They're often selected when a project wants stronger visual impact or ecological value, but doesn't need or can't support a fully programmed park-like roof that you would see in like an extensive roof system. Architecturally speaking, these systems work well for pollinator meadows, decorative landscapes, and lightly accented roof areas. They represent a deliberate step up in complexity and expression without the full cost of coordinating demand of an intensive green roof. Here's an example of roof with native seeding plants. A little bit of performance with the semi-intensive. The defining characteristic of a semi-intensive green roof is performance driven by additional growth depth. That added soil adds volume in several important things simultaneously. It increases the stormwater retention, improves plant health, moderates rooftop temperature extremes more effectively than an extensive system. And from a stormwater standpoint, deeper substrates hold more water and release it more slowly. This reduces peak runoff during storm events and improves overall compliance with municipal stormwater regulations. In cities where detention requirements drive design decisions, semi-intensive systems often provide a meaningful advantage without requiring underground infrastructure or oversized cisterns. Plant performance also improves significantly. With more root volume, plants experience less stress, establish more reliably, and recover quickly from drought or extreme heat. This results in heavier vegetation, reduced plant replacement, and better long-term appearance. This is especially important when the roof is visible from adjacent buildings or accessible for limited use. Thermally, semi-intensive roofs provide stronger buffering than an extensive system. The added mass above the roof assembly dampens temperature swings. It reduces heat gain in the summer and slows heat gain in the winter. While this may not drastically change HVAC sizing, it contributes to improved comfort and energy savings for the life of the building. From an architectural decision-making standpoint, semi-intensive systems represent a deliberate step up in performance expression, and they are commonly selected when a project needs more visual richness or ecological value than that of an extensive roof, but cannot support or justify weight, cost, coordination of a fully intensive roof. Now moving on to intensive green roofs. So an intensive green roof system represents the highest level of investment and complexity possible when dealing with vegetated roofing system. They function much more like a conventional landscape that happen to be located on a structure, whether it be a roof or an amenity deck. It could go multiple ways. These systems typically include deeper soil profiles, often well beyond 12 inches, along with the permanent irrigation, hardscape elements, and fully walkable features. Because of this depth and functionality, intensive roofs are designed for active, regular use. They often include seating areas, walking paths, planters, trees, weather features, and other programmed elements. From an architectural standpoint, these roofs are true amenity spaces, and they should be approached with the same level of design rigor as that of a ground level or plaza courtyard. Structurally, intensive green roofs require early coordination. The additional soil depth, hardscape required, saturated weight, and live loads all have a different impact on the structural integrity of your enclosure. These considerations need to be addressed very early in the design, as you know, and as they can significantly influence slab thickness, framing strategy, and overall building cost. From a systems perspective, irrigation and drainage become critical components rather than an optional enhancement. Intensive roofs rely on consistent irrigation to support plant health, and they require robust drainage planning to manage the larger volumes of retained and released water. Maintenance access, safety, and long-term operational planning must be clearly defined and communicated to the ownership. Architecturally, intensive green roofs offer the greatest flexibility and expressional value when designing a roofscape, but they also carry the highest expectations. They are best suited for projects where roof access, landscape quality, and user experience are key project drivers. When designed and coordinated properly, intensive green roofs can become some of the most successful, highly valued spaces in a building, but they also require a clear commitment to structure, maintenance, and a long-term care for the outset of the overall system. So the biggest advantage of intensive systems is flexibility in planting, programming your amenity space, and usability. They offer insulation benefits and high amenity value. Intensive green roofs provide the most flexibility in terms of planting and programming, allowing architects to create true outdoor rooms at the roof level. These systems can accommodate trees, shrubs, circular plant paths, water features, and social spaces, turning the roofs into an extension of the building's usable program and often becoming a signature amenity. However, these benefits come with equally important trade-offs. Intensive green roofs include significantly higher dead loads due to deeper soils, hardscape elements, and saturated conditions. These live loads from occupants and furnishings must also be considered. This has a direct impact on structural design and often requires early decisions around slab thickness, framing, and building cost. Finally, intensive roofs can carry the highest maintenance expectations. Unlike extensive or semi-intensive, they cannot be allowed to run hands-off. Long-term plant care, irrigation management and upkeep, seasonal upkeep, and access planning must be clearly defined and communicated to the ownership from day one. When owners understand and commit to that responsibility early, intensive green roofs can perform exceptionally well. When they don't, these systems can quickly become costly and problematic. Clear alignment between design intent, structural capacity and capability, budget, and long-term maintenance is what ultimately determines the success of one of these systems. Before I move on to protecting waterproofing, though, this When green roofs fail, they rarely fail because of the plants die. They fail because of the waterproofing system below is damaged, inaccessible, or it was inadequately installed. Long-term success starts with selecting a durable waterproofing system that is compatible with a vegetated assembly. Green roofs are not only the place of the value engineer and the membrane. Whatever goes below the soil needs to be built to outperform the rest of the building envelope because access for repair is difficult, disruptive, and expensive. Protected membrane roof assemblies are central to this approach. By fully covering the waterproofing, eliminating exposed membrane, you shield it from UV degradation, thermal shock, and physical abuse. The overburden essentially becomes the protection layer, dramatically extending the membrane's service life and reducing your risk over time. Vegetated-free zones are equally critical, which we'll get into in a second. But vegetated-free zones are equally critical. These zones keep soil and plant material away from flashing, penetrations, perimeters, and drains. Most importantly, they provide clear, permanent access for inspection and maintenance. If flashing cannot be seen or accessed, it cannot be maintained, and that's where small issues become failures. The drain inspection chambers are often a non-negotiable element to a green roof system. Drains must remain visible, serviceable, and free-flowing for the life of the building. Buried or obstructed drains are a leading cause of ponding water, which increases hydrostatic pressure and stresses the waterproofing. And finally, long-term success requires acknowledging that green roofs are living systems, layered over critical waterproofing. Routine inspection and maintenance are not optional add-ons, they are part of the design intent. When durable materials, protected assemblies, clear access zones, and maintained planning come together, green roofs don't just succeed, they outperform conventional roofs both technically, financially, and performance-wise. If the waterproofing fails, everything else above it fails. Soil, plants, hardscape, and amenities, immediately becoming a liability. Designing for protection and access from day one is what separates successful green roof projects from ones that generate callbacks, leaks, and unfortunately litigation. So now we'll go into the green roof systems as layers. So this is where everything we've been discussing so far comes together. A green roof should always be thought of as a fully coordinated system of layers, not just a collection of interchangeable products. Each layer has a specific job, and more importantly, each layer exists to protect the layer below it. Starting at the very top, we have the vegetation. While this is the most visible part of the system, its success depends entirely on what supports it below. Immediately below that, you'll have the growing media and the soil, which, as we discussed earlier, is engineered to balance weight, drainage, and nutrition and retention. If the wrong material is used here, it could overload the structure, it could clog drains, or stress the plants. Below the growing media, you'll see the filter fabric and protection course. This layer is critical for long-term performance because it prevents fine particles from migrating downward. Without it, fines wash into the drainage layer, reducing the flow capacity and eventually leading to ponding water, one of the primary causes of a membrane's failure. Next, we have the drainage composite. Now, there are a couple different kinds of drainage. The drainage you select depends on the type of roof system that you're designing, but this layer manages excess water, ensuring that it is directed to roof drains while still retaining enough moisture to support plant health. And for architects, this is a key consideration point because the drainage performance directly affects both plant success and your waterproofing membrane's longevity. Below the drainage layer sits the insulation, often XPS, in protective membrane assemblies. XPS is moisture resistant, protects the membrane, and just helps shed that moisture away. In this configuration, the insulation seals the waterproofing from temperature extremes and mechanical damage, helping maintain consistent performance over time. Directly underneath the XPS, we have our root barrier, which prevents aggressive root systems from penetrating or compromising a waterproofing's membrane. And while it may seem like a redundant layer, this is absolutely critical in the long-term safeguard of the other components listed into this assembly. And finally, at the heart of the system, we have the waterproofing membrane itself. This is the single most important layer of the assembly, and I really can't stress that enough, because since everything is above it and is difficult and expensive to remove, the membrane must be continuous, durable, and fully compatible with a vegetated roof assembly. Most commonly, in vegetated roof systems, hot rubberized asphalt, and they perform exceptionally well, particularly in protected vegetated assemblies. Their thickness, the flexibility, and fully adhered monolithic nature of them makes them highly resistant to punctures and movement. Not to mention that during when install, waterproofing contractors will come in, put the hot rubberized asphalt down, lay a protection course on, and then other phases and trades throughout the project, they could work on top of that membrane while it's protected. When the waterproofer comes back, just does a spot check, make sure everything is good, and keeps on going. So because they are seamless, they perform exceptionally well at complex conditions such as drains, penetrations, and transitions. Areas where green roofs place the highest demands on waterproofing systems, and also for complex detailing, they're compatible with cold applied systems like Pumas or PMMA. So when you have areas where you really can't work with get the hot applied material around, let's say, piping conduits or anything like that, PMMAs are another option. They're completely compatible with the hot applieds as long as you follow in the manufacturer's installation details. And then finally, all those layers sit on a structurally sound roof deck, typically concrete and green roof applications, which provides that non-combustible deck, stable substrate required to support the full system. When these layers are specified, detailed, and coordinated correctly, they work together as one integrated assembly rather than competing components. Going into the drainage composites, there's many different options. Basically, you're going to choose the drainage board that fits your vegetated roof assembly. So an extensive roof assembly will have a shallower dimples, but then your intensive will have deeper ones just to retain more water to withhold the plant life. So going to XPS and then vegetated free zones. So we're going to be spending a bit of time on this because I can't stress the importance of this crucial detail. So vegetated free zones are often underestimated in design, but they play the most critical role in long-term performance and livability of a green roof system, especially when you consider the maintenance requirements. These zones are intentionally kept free of growing media and vegetation to protect critical waterproofing details such as flashings, penetrations, perimeters, and drains. By restraining soil and plant material, vegetated free zones reduce risk of root intrusion, moisture retention against vertical surfaces, and damage to the flashing details over time. Equally important, VFZs provide safe and reliable access for inspection and maintenance and repair. They create clear pathways for service personnel to reach drains, mechanical equipment, and roof edges without disturbing the plant area or compacting the growth media. This access is essential for routine maintenance tasks and for addressing issues before they escalate into costly failures. For these reasons, VFCs should be not viewed as a leftover space, but as an intentional design. And they are risk management features that protect the waterproofing system, support proper maintenance, and significantly reduce long-term liability for the design team and the building owner. And you'll see that with these vegetated free zones listed here, you have a lot of flexibility on where they go, just as you have flexibility with what your drains are, because drains come in all shapes and sizes, but also maintaining VFCs around detailing around equipment. So unlike planting areas, your mechanical and rooftop equipment will be accessed repeatedly over the life of your building. Units are serviced, filters are changed, belts are replaced, and in some cases, pieces of equipment are even swapped out. If the design does not clearly accommodate that reality, maintenance activity ends up damaging the green roof system. Vegetated free zones around equipment provide intentional, durable buffer zones that keep soil and vegetation away from curbs, penetrations, and vertical flashing transition. These areas protect the most vulnerable parts of the waterproofing system from repeated foot traffic, tool impact, and vibration during equipment servicing. For a maintenance standpoint, VFCs are absolutely essential. If service personnel are forced to step through the planting or walk directly onto the flashing to reach equipment, the green roof can be damaged over time. Guaranteed. I can guarantee that. This issue is rarely a single event. It's cumulative wear from routine maintenance that slowly degrades plant performance and flashing integrity. Well-designed vegetated roof-free zones define where people are supposed to walk. They create safe, predictable access paths using aggregates, pavers, or other durable surfaces. And when those paths are clearly defined, maintenance crews naturally follow them. When they're not, Crews take the shortest route, which almost always cuts through planting and across sensitive detailing. And then these zones also matter during emergency or winter conditions. When equipment needs to be serviced in poor weather or low visibility, maintenance staff should not be navigating through vegetated areas or guessing where they could step. VFCs provide a clear, repeatable access that protects both the green roof and the people maintaining it. Architecturally, it's important to understand that VFCs around equipment are not aesthetic compromises. They are absolutely risk management details. Projects that minimize or eliminate these zones offer experience repeated plant damage, displaced growth media, clogged drains, and deterioration of flashing details around curbs and penetrations. The key takeaway here is simple, but important. Vegetated-free roof zones around roof equipment are not an optional clearances. They are essential maintenance infrastructure. When they are properly sized, located, and detailed, they allow building systems to be serviced without managing green roofs or creating long-term liability for the design team and owner. A couple more examples of vegetated-free zones. So, you have options. You could use roof pavers, ballasted gravel. There's a nice little deck detail there. And then, another main use for vegetative-free zones and these vegetated roof systems are to protect drain chambers. So these next slides, I'm going to focus on one of the most common and most preventable causes of green roof failures or green roof calls, that are roof drains that are buried, inaccessible, forgotten over time, or just flat out incorrectly detailed. So no matter how well the planting system performs, a green roof cannot function if water can't reliably leave the roof system. So in this picture you see here, these drains are right to the deck, and you can see how the membrane kind of ties up and over and makes the whole drain bowl assembly part of the flat waterproofing membrane. So when water gets into that, it guides it down into the drains. You'll see that this is on the bottom of this system, right? So the system is built up and around it. So on a vegetated roof, you lose the visual cues that you get from a conventional roof. You can't easily see ponding water or clogged strainers. You can't easily see the slope because everything is covered. And that's why drains on green roofs must always remain visible and serviceable for the life of the building. This is the role of the drain inspection chamber. These chambers are created to protect open zones around each drain, keeps the soil, roots, and debris away from the drain body while still allowing free movement of water. Just as importantly, though, they give maintenance staff a clear intentional access point for these drains as part of the routine. So very simply, pop the cover off the drain, and then your drain is completely accessible. You don't have to remove parts of the assembly, parts of the overburden. Easy peasy. So, and also architecturally, this is where performance and risk management intersect. These buried drains are leading cause of prolonged ponding water, and ponding increases hydrostatic pressure on the waterproofing membrane, stressing the seams, penetrations, and transitions. Once water is trapped below the planning system, locating the root cause and making repairs becomes disruptive and expensive. The takeaway here is simple and very much worth repeating. Every drain on a green roof must be treated as a permanent access point, not something that gets covered up later. When drains remain visible, accessible, and routinely inspected, green roofs perform as designed. When they don't, even in the best waterproofing assemblies, are placed under unnecessary stress. And this exactly right here is what you want to avoid. Easily avoidable with just designing a drain gate protection area around your vegetated free zone. Drains come in all different shapes, sorts, and sizes. So, you really have design flexibility on how whichever drain you're specifying needs to fit within your assembly. Now we'll move into growth media. So green roof growth media isn't just your average topsoil. It's very highly engineered. It's designed to be lightweight, free draining, and properly balancing for nutrients. Unlike your conventional topsoils, it is typically a blend of mineral aggregates and organic material that provides consistent structure, resists compaction, and allows excess water to drain efficiently while still retaining enough moisture to support plant health. This balance is critical on a roof, where saturated weight, draining performance, and long-term sustainability directly impact both structural loading and waterproofing performance. Planting strategies vary depending on depths of the system and maintenance expectations. Sedum mats provide immediate coverage and erosion control, while plugs and cuttings allow for greater design flexibility and establishment over time. Modular or tray systems offer pre-grown vegetation and can simplify installation when access is limited. Though they introduce additional considerations around drainage, continuity, and long-term maintenance, regardless of that approach, plant selections and installation methods should always align with the intended roof use. Irrigation strategy and the owner's ability to maintain the system long-term are also exceptionally important. Maintenance responsibilities. Now, like I mentioned earlier, these green roofs, they do require constant and scheduled maintenance in order to perform as intended. These green roofs, they're living systems. And like any landscape, they require ongoing care, especially during the first 1 or 2 years after the installation. This initial establishment period is absolutely critical. Plant material is still rooting, irrigation systems are being fine-tuned, and the growing media is settling. Most early failures, whether plant loss or drainage issues, can be traced back to insufficient maintenance during this window period. Routine maintenance tasks are straightforward but essential. Drain and inspection chambers must be kept clear, must be inspected regularly so that water can move freely through these systems. Vegetated-free zones should be regularly checked to ensure soil and plants have not migrated into flashing areas or into the drain itself, as you've seen in some of our picture examples here today. And vegetated-free irrigation systems should be adjusted seasonally to account for plant establishment, weather patterns, or seasonal changes. And equally as important as adherence to the operation and maintenance manuals provided by system designers, installers, and manufacturers, these documents outline acceptable practices, inspection intervals, and prohibited activities. When maintenance guidelines are followed, the green roof protects both the planting system above the waterproofing and below the waterproofing membrane. When they are ignored, small issues can escalate quickly into costly repairs and warranty concerns. Now moving on to warranties. So most full green roof assemblies include long-term waterproofing warranties, typically on the order of 20 years, while plant warranties are usually much shorter. The difference is intentional, and that it's important for designers to understand what each warranty actually covers. So typically your waterproofing warranty is focused on the performance of the membrane and its related components in the assembly below the overburden. And when properly detailed and protected, as we've been discussing, this membrane is expected to perform for decades. Because access is limited once a green roof is installed, manufacturers place strict requirements on system selection, detailing, inspection, job intermittent site visits as well, and protection in order to stand behind long-term warranty. The plant warranties, by contrast, are typically more limited than that of the waterproofing membrane. That's because the vegetation is a living organism, and in long-term plant success depends heavily on maintenance, irrigation, water, and the owner's care. Once the establishment period ends, ongoing plant health is no longer a warranty issue. It becomes an operational responsibility. And this is where clearly defined owner responsibilities are critical. Maintenance requirements, inspection intervals, and access provisions must all be spelled out clearly in the O&M documentation and communicated to the ownership at the turnover. Many waterproofing warranties are contingent on regular inspections and documented maintenance, so that's something to consider. And from an architectural risk standpoint, alignment is key. When your owners understand what is warranted, what is not, and what is required to maintain coverage and what is prohibited on your roof system, green roof systems perform as intended. When those expectations are clearly not set, warranty coverage can be jeopardized even if the system was installed correctly. So these standards listed up here on the screen from ASTM, ANSI, SPRI, and FFL form the technical backbone for proper green roofing specifications and detailing. They're not there to complicate the design process, but to enhance shared framework around performance, durability, and long-term risk. ASTM standards help to define material properties and testing criteria, ensuring that components perform as expected, When they are part of the layered assembly, ANSI, SPRI standards are especially important for vegetated roofing systems, addressing membrane performance, wind resistance, and assembly integration. And the FFL guidelines, while European in origin, are widely referenced because they reflect decades of field-tested green roof experiences, particularly around system layering, drainage, and planting strategies. When your details align with these references, you're no longer relying on a one-off solution or untested assembly. You're anchoring your design and decisions in standards that manufacturers, consultants, and owners all recognize. From the architectural liability standpoint, that alignment matters. It demonstrates due diligence and long-term exposure. In practice, it means coordinating with every consultant, confirming system compatibility, your contractor and manufacturer, and the detailing critical conditions like membrane protection, VFCs, and drain access. In ways that follows established guidance when those fundamentals are in place. Green roofs perform predictably and successfully over time. And that concludes our presentation for today, but I would like to close with this. So green roofs don't fail because plants grow or don't grow. They fail when systems aren't coordinated, when access isn't planned, and when responsibility isn't clearly defined. As architects, your influence is greatest early. When assemblies are selected, details are drawn, and expectations are set. These decisions you make around membrane protection, vegetated-free zones, and drainage access and maintenance pathways are the difference between a green roof that quietly performs for decades and one that becomes a long-term liability. A successful green roof isn't an architectural gesture. It's true infrastructure. It's a roofing system first and a landscape second, and a maintenance responsibility for its entire lifespan. When those realities are acknowledged and designed up front, green roofs deliver real value, environmental, financial, and technical value as well. If there's one lesson from today, it's this. When you design green roofs as robust systems instead of merely decorative layers, you mitigate risk, safeguard the waterproofing, and create assemblies that fulfill their intended purpose. And with that, I would like to thank you very much for your time and attention today.